Okay. So heat can be positive, it can be negative. Positive means it's going into the reactor. Negative means it's going out of the reactor. So let me draw you a little picture to sum all this up. Here's your reactor. So work can go in. And if it goes in, it's positive, and that means it's done on the reactor. Work can go out. And if it goes out, it's negative, and that means it's done by. It's done by the reactor. And then you have a sign convention for heat. Heat can go in, and if it goes in, it's positive, and we call that endothermic. And heat can go out, and if it goes out, it's negative, and that's called exothermic. Where does it go? Into the water. Where does it come from? It comes from the water. Okay. So there's our sign convention. Any questions about the sign convention? Those are the only two that you have to worry about at this stage. I'll leave that up there just for one more minute, and then I'll create a new slide here. This is the essential info that you need to do these problems. Okay. Now, we're going to put it all together, work and heat. And what we're going to claim is the following, that if you have a reactor, a place where a chemical reaction is taking place, there are only really two ways that energy can go in or out. Energy can go in, and it can go out. And so we're going to call the net delta U. We're going to call this the net energy change. Okay, meaning how much energy went in, how much energy went out, what's the difference between the two? And we're going to say this delta U is called Q plus W. And this is the important formula that you have to remember. It's really the only formula that I've given you so far in this. Delta U, the net energy change, is equal to Q plus W, the two terms that we've just been talking about. So again, it's not a bad analogy to think of this as money. So if you have a bank account, money can go into the bank account. So let's say $500 goes into your bank account, but then $300 goes out, right? The net change would be 500 minus 300. So positive 200, right? That's essentially what we're doing with these heat and work problems. We're saying that there's two ways that energy can go in or out. The first one is heat, and the second one is work. So we need to know both of those values to figure out what the net change in energy is. So this delta U has a term, it's called the change in internal energy of the reactor. And some textbooks will use delta E. It's perfectly fine to use delta E. Delta U is more common, but those essentially mean the same thing, okay? And the way you calculate it, the way you calculate the change in energy or the change in internal energy is you figure out what Q is, and you make sure you get the sign right. You figure out what W is, and you get the sign right, and then you add those two together, and that will give you the change in energy, the change in internal energy. And that is essentially what the Aleks problem looks at, is having you figure out, maybe they give you this one and they give you this one, and then you have to figure out that one. Or maybe they give you this one and they give you this one, and then you have to figure out this one. But they're going to give you two of them, and then you have to figure out what the third one is. Okay. So let's take a look at an example. The math is ridiculously simple, but the terminology can be confusing. Okay. Let's see here. Oops. Here we go. All right, so the one I'm going to look at, this is an Aleks problem, and their diagram is a little more complicated than I typically draw them, but it looks something like this. Okay, so this is an insulator just to trap the heat so the heat doesn't get out very easily. And then inside is this little reactor. So there's your piston. These are the gases in the reactor. And then they put a little thermometer here to measure the temperature of the water. So there's water in here. Okay, this is a water bath. Okay, so that's the cylinder and the piston. There's your piston. And then you go through this problem. So here's what they do. They say you put this in here, and the reaction, oops, this is the information they give you, absorbs 316 kJ. That means kilojoules. That's a unit of energy. Okay. 316 kilojoules of energy. Okay. The reaction absorbs 316 kilojoules of energy. So that's the first piece of information they give you. Then they give you another piece of information. They tell you that the piston does 283 kilojoules of work on the system. So you really have to be careful when you calculate these things, okay? So then they ask you several questions. They're really going to get you at this. The first one is the reaction endothermic or exothermic? Okay, that's the first question. Is it endothermic or exothermic? 2, does the temperature of the water go up or down? The third one, does the piston move up or down? And then the fourth one is, actually there's 5 questions. Does, oops, this is 4. Does heat flow into the gases or out? Does it go in or out? And then 5, how much heat flows in kilojoules? Okay, so there's a lot here. There's a lot of questions, and this really gets very deep into the understanding of what's going on. So you have to really break this apart into separate components. So here's what we're going to do. We're going to look at one at each step. So the first question is the reaction endothermic or exothermic? And one of the things that's a little tricky about this is that it's not obvious. You have to actually calculate it. Okay, so let's do question 1. Is it endothermic or exothermic? So remember what we said is if it's endo, that means Q is positive. Heat is positive. If it's exo, Q is negative. So we look at the information. It says the reaction absorbs 316 kilojoules of energy, but that doesn't say heat. So that's not heat it's talking about. If it said it absorbed 316 kilojoules of heat, we would have our answer. But it just says energy, not heat. It also says the piston does 283 kilojoules of work on the system. Again, that's not heat. So we don't know what heat is in this problem. We cannot answer this question here until we know what the heat transfer is. So here's what we're going to do. We're going to calculate it. The only equation you really need for this type of problem is delta U equals Q plus W. Okay, heat plus work. This is energy. This is heat. This is work. We want to know what heat is. So we have to find Q. So here's what we do. We rearrange this equation. If you want Q, you subtract W from both sides, right? Q plus W minus W is Q. So you subtract delta U minus W, and that gives you Q. So now let's go through it. We do know it absorbs 316 kilojoules of energy. That's your delta U. Energy is delta U in these problems. And it absorbs. Absorbs means it's coming in. That means it's positive. So this is positive 316. Then we got to subtract W. Well, let's see what W is. The piston does 283 kilojoules of work on the system. The system is the reactor, the gases. Okay. This is the system here. The system is what we're interested in. So if 283 kilojoules of energy of work is being done on the system, that means that W is positive. On the system, that's the terminology that we used earlier. So that means it's positive. So 283 kilojoules. So 316 minus a positive 283 is equal to Q. Now we just do the arithmetic. That would be what? 17 plus 16 is 33. That would be 33 kilojoules. Positive, because 316 is greater than 283. And there's your answer for, this is actually the answer of number 5, but it also gives us the answer for number 1, because the question is Q positive or negative, right? Endo is positive, exo is negative. Well, it's positive. So if it's positive, that means it's endothermic, right? Q is positive when it's endothermic. So our answer is, for question 1, it's endothermic. But we also get the answer to question 5. It's 33 kilojoules. So we also have that one as well. So question 1 is done. It's endothermic. Question 5 is done. It's 33 kilojoules of heat is flowing into. So here's what happens. They give you these numbers. And now what we're saying is, based on these numbers, we've calculated that energy is going into the system, which is the reactor, the gases. It's going in there in the form of heat. It's an endothermic process. Heat is going in, okay? Now, temperature is not a difficult question to answer here, and here's why. If you have whatever it is, it could be an ice cube, it could be a battery, it could be your body. If heat goes into something, it gets hotter. We have that intuitively in our experiences in life. If heat comes in, you get hotter. If you get hotter, that means the temperature goes up. Okay? Heat in, you get hotter, temperature goes up. So as heat goes in, temperature goes up. If heat goes out, temperature goes down. What did I write? Go in. I don't know what I just wrote there. I'm sorry. As heat goes in, temperature goes up. As heat goes out, temperature goes down. You know, on a cold day, just open up your window, heat will go out, the temperature of your room will go down. Close the window, turn on the heater, heat comes in, temperature goes up. So that's actually relatively simple. If heat is coming in, it's endothermic, then the temperature of the gases should go up. But the question then here is they're asking about the water. So this is tricky. Be very careful. If heat is going into the gases, the question is, where's that heat coming from? And the answer is it's coming from the water. So be very careful. They didn't ask about whether the temperature of the gases is going up. They asked about the temperature of the water. And heat goes from the water to the gases. So if the gases are endothermic reaction, that means heat's coming in, it's got to be coming from the water. So that means the temperature of the water is going to go down. Okay, so be careful about that. Typically, they will ask you the temperature of the water, not the actual reactor. So you have to do the opposite. Okay, so that's question 2. The next issue is, does the piston move up or down? And that has to do with work. Okay, so heat is temperature, exothermic, heat going in, heat going out. Work, W, is the piston moving in or out. And sometimes be careful, they may say up or down, or they may say in or out. Because what happens is if you have a piston and you turn it around, if you just flip it on the backside, what used to be going up would now be going down. So the terminology up and down is not always used. They'll say in and out. So if it's in and out or up and down, really what they mean is for the piston, so this is the piston I'm showing over here, it's either going up or it's going down, and that could be down or in. If it's going up, that's the same thing as out. Remember, the gases are in here. So for that one, here's what happens. When a gas expands, expansion of the gas, that means the piston's going up or out. If it's being compressed, that means it's going down or in. Okay, so let's take a look and see what happens. It says the piston does 283 kilojoules of work on the system. Okay, I'm going to actually save this because I'm running out of room. So the idea is this. Here's your piston. This is the piston here. And these are the gases inside there. The convention again is if the piston goes in, if it goes to a smaller space, a smaller volume, so now we're this is called compression. W is positive. So in or down, W is positive. And that the terminology that they will use is work is being done by the piston. Okay, work's being done by the piston. So that would be positive. The opposite is, here's your gases. It's expanding. So this is called expand. There's the piston. This is called expansion. And there we would say it's going out or up, and W is negative. And here we would say work is done on the piston. On the piston, and that would be negative. So let's go back to the previous one. Which is right here. It says the piston does 283 kilojoules of work on the system. Well, what that means is the energy is going into the system. So W is positive. Okay. So we can say, does the piston move? Well, it's positive right here. Does it move up or down? Well, that's what I just told you the convention is, right? The convention is if work is done by the piston, then it's going to be positive. Okay, so since it is positive, that means work is being done by the piston. And if it's being done by the piston, that means it's compression, and that means that the gases are going to be compressed. Okay. So let's see. Does the piston, so it's going to move down. So there's our answer there. So down, sorry, there's not much room here, would be our answer for that one. Okay. So really, there's only one question about work in this whole problem. The last one, which kind of we answered, but I haven't looked at it formally, is does heat flow into the gases or out? We kind of already answered that. Essentially, what's happening is we figured out Q is positive. If it's positive, that means heat is going into the gases. So the answer there is it's going, this is question 4. Heat flows into the gases. Okay. So that's pretty involved. And if you take a look at these problems, they're multi-part. There's like 5 parts that you have to answer for this question. So you're going to have to get used to the language there. Once I get this uploaded, you can watch this video of my explanation of that problem as many times as you want. The terminology is really the hardest part of this. This really gets into how well do you understand the language that we're using. It's really a language problem. Flowing in, flowing out, heat, work, the sign convention. But it's pretty challenging. That's a tough problem. So that's, in my opinion, that's the toughest problem in this chapter. And so if you really want to get good at it, you'll have to practice it a few times. Okay. Looking at the explanation that they give, their symbols are a little bit different. So the symbols they use, I used this because this is what your textbook uses, and I try to go by what the textbook says. I use those symbols, but Aleks uses different symbols. They use delta E, and then they use capital Q and capital W, uppercase. All right, so they're using Q and W, but they're using uppercase, and then they're using delta E instead of delta U. Okay. All right. Now, what I want to show you is there is a type of problem where you have to calculate the work done involving a piston.
Can I ask a quick question?
Sure.
Does the heat of the gas always, is the temperature of the gas always the opposite of the temperature of the water?
Yes. And the reason is that what we're doing is we're separating everything into two parts. The system, which you can think of as a battery, and the surroundings, which you can think of as the light bulb. So if the light bulb takes energy from the battery, that means the battery's losing energy. So its temperature, might go down, and the temperature of the light bulb might go up, right? So they always do the opposite.
Thank you.
Mm-hmm. Okay. The one I want to show you here is calculating the work involving a piston. So again, our piston is right here, right? When they say piston, what they mean is a cylinder. Okay, and then you got your gases. Okay, so this is the piston. The whole thing is called a cylinder. This is actually how automobiles work, right? What you do is you spray in a mixture of air, which has oxygen, and gasoline vapor, a very small amount of gasoline vapor. And what happens is that oxygen in the air mixes with the gasoline vapor, and then you have a spark plug, which just like ignites it, and it burns very, very rapidly. As it burns, what it does is it gets hot. And as it gets hot, it pushes the piston up. And then that piston is connected to mechanical devices like gears and cams that allow rotation to occur. So you're converting the energy into rotational energy, and then that drives the drive shaft and the drivetrain. And so the automobile can run. But it all comes down to this idea that you take oxygen, which is out of the air, you suck it out of the air, you take the gasoline vapor, you vaporize it just by spraying it into an aerosol, essentially. They mix together in a cylinder, and then the spark plug puts in a little bit of electrical energy just to ignite the reaction. It reacts and then pushes the piston out. And that conversion to mechanical energy work is the work that gets used to drive the automobile. Okay. So when you buy a car, one of the things they will tell you is how many cylinders it has. How many of these? Typically, it's an even number. So it could be 4, it could be 6 or 8. I think there's one, what are they? I forget the name of the company. Those like expensive cars, not Volvo, Saab, I forget. One of them, they sell 12-cylinder cars, but typically it's 4 or 6, sometimes 8. The size of the cylinders are typically given. So if you buy a car that is a 2.0 liter engine, really what they're telling you is the sizes of these pistons, what the volume of those pistons are. And they're typically in metric units. So typically you'll see 1.6 liter or 2 liter. And that's really telling you how big these pistons are. So they're not very big, really. Really, they're like, the size of a glass, but you might have 4, 6, or 8 of them. And so altogether, the total volume might be 2 liters. Okay. So let's take a look. This is actually a very simple type of calculation. Here we go. So what they tell you here is you have a mixture of gases. Expands from a volume of 34.0 liters. There's that liters, right? So that's actually a big volume. Like a pretty powerful car is only like 2.5 liters. This is a much larger volume. To a volume of 92.0 liters. While the pressure is held constant at 33.0 atmospheres. That's a very high pressure. Okay, remember the Earth is at 1 atmosphere pressure, so that's a pretty high pressure. Calculate the work done. On the gases. Okay, now in this problem, they tell you it's helium and they tell you it's hydrogen, but that's not important for this type of problem. It doesn't matter what the gases are. Okay, so you have these gases in here. Now, when they say that the pressure is held constant at 33 atmospheres, really what they're doing is they're telling you that in this cylinder, in this piston, there's a pressure pushing down. And that's the 33.0 atmospheres. So if the gas is going to expand, right? You know, this is essentially Newtonian physics. If the gas expands, the gas has to produce a pressure that's equal to 33 atmospheres. So if it can produce a pressure that's equal to 33, it'll start pushing the piston up. So that pressure, P, I'm going to write that down. So these are the units, atmospheres. And then this is the value of the pressure. And the symbol we're going to use is P. This is pressure. Okay. And then what we have, notice we have two volumes, 34 and 92. There's two different volumes. So what they're doing is they're saying, what is the volume before? And that's 34. And then what's the volume after? The total volume at the end, 92.0. Okay. So what happens is you start with an initial volume and then it expands to a final volume. If it expands, that's like pushing a brick up. That takes energy, and that energy is called work. So very simple formula. I'm going to say V for volume 1 is where we start. That's our initial. And again, you know what liters are. A 1 liter bottle, a 2 liter bottle. This is 34 liters. The final volume, V2, 2 for final, is 92 liters. Okay, so we're expanding. So here's the formula. This is the formula you got to use. The work for this type of problem is minus, it's got to have a negative in front of it, P times V2 minus V1. Sometimes this is written as minus P delta V. You'll see it this way as well. When it's written that way, what they mean is that delta V is V2 minus V1. That's what they mean by that. Okay. So we're almost done. Now we just got to do the calculation. Don't forget the negative. P is W is minus P. So what's P? 33.0 atmospheres. And then what's V2 minus V1? 92 liters minus 34 liters. Okay. So let's do that calculation. 92 minus 34 times 33, and you get negative 1914. What are the units? Atmospheres times liters, because you're taking P and you're multiplying it by delta V. So atmosphere liters. So it has sort of odd units. Typically, they don't want the units to be done in atmosphere liters. They typically want them to be done in either joules or kilojoules. So I'm going to show you what the formula for that is. So W, don't forget the negative. 1914 atmosphere liters. Here's the conversion that you need. The conversion is 101.3 joules is 1 atmosphere liter, or 101.3 kilojoules is 1,000 atmosphere liters. So if they want the answer to be in joules, you can use this one. If they want it to be in kilojoules, you can use this one. All I did was I took the first one and multiplied by 1,000. Because remember, a kilo is 1,000. So let's do this problem. Minus 1914 atmosphere liters. So there's your work. Now we're going to use the conversion. Let's do it in kilojoules. I'll do this one right here. We want to get it to kilojoules. So we want this in the top. We want to get rid of atmosphere liters. So we want this on the bottom. So times 101.3 kilojoules per 1,000 atmosphere liters. Okay. So now the atmosphere liters cancel, and you're going to have kilojoules. So it comes out to 1914 times 101.3 over 1,000. Don't forget to divide by 1,000. So you get negative, negative 194 kilojoules. Notice it's negative. So they don't ask this in this particular question, but remember the first one, we had all those 5 parts and there were all those issues that you had there. So for this, we would say the piston moves out, or the piston moves down. Remember, out is the same as down. Okay, that was our sign convention. If W is positive, the piston moves in. If W is negative, the piston moves out or down. I'm sorry, up. My apology. In or down. Okay, that's our sign convention that we had earlier. So that since we calculated it as being negative, that's what happens. So the idea here then is the piston. Think of the pressure like a force pushing down. Okay. It starts off at 34 liters, and then something happens so that the piston now has a volume of 92 liters. It still has that pressure pushing down, 33 atmospheres. And so what we would say is this is expansion. Piston moves out. Okay. And so negative, that's what happened. And the reason it's negative is, remember this formula? It has that negative in it. You don't see a lot of problems like that in probably the calculations you've done in other classes, but this particular equation has a negative in front of it. And so that negative affects what your answer is going to be. So be aware of that one. Okay. So that's only 2 problems I showed you. But remember that first one I showed you is a very lengthy and very complicated problem. So when you do these problems, you'll probably do the second one first. This will come up first. And so this one's a pretty easy little calculation. But that second one will come a little bit later and you'll have to work through that one. Okay, so dedicate a little bit of time to that second type of problem. I mean, factor it in that you're going to have to spend some time on that one. Because again, it's 5 questions in one, so it's a pretty complicated problem. So we talked about that. So what we need to do tomorrow is to talk about enthalpy, which is section 5.3. And then we'll go a little bit into calorimetry, which is section 5.4. And then on Thursday, we'll do standard enthalpies of formation, which is a relatively simple problem. We'll look at that on 5.6. There aren't as many topics in this chapter. There's only 13. And you compare that to chapter 3 where there were 22. But of those 13, I would say 3 of them are pretty hairy type problems. They're pretty involved. So you want to make sure you have time to do those 3. And some of them are pretty simple, but 3 of them are pretty challenging. Okay. Very good, everybody. Thanks for showing up today. And if you have any questions, let me know. Get in touch with me. If you need an office hour this week, let me know, and we can look at some problems together. Okay.
Thank you.
Have a
When will
great
you be
day.
posting?
Have
when
a
will you
great
be
one.
post-
Say that again.
When will you be posting this video?
Oh yeah, because I just noticed before we came in that I
Professor.
forgot to post yesterday's. I'm gonna post yesterday's and today's in the next it's like half hour. It takes about a half hour, or it takes about 20 minutes for it to do it. So about a half hour.
Okay, thank you.
Very good. Take care.
Thank you.
Absolutely.